In orbit, roughly 525 kilometers above Earth, a small experimental satellite converted sunlight into electricity, sent that electricity through a microwave transmitter, and beamed it across open space to a receiver positioned about a foot away, lighting up a small pair of LEDs. It sounds almost trivially small. It was, in fact, the first time in history that wireless power transfer had been successfully demonstrated in space, a genuine engineering first achieved by a team at Caltech, and the opening move in what's rapidly becoming a real international race. The concept of space-based solar power isn't new. NASA engineer Peter Glaser first outlined the idea in 1968 article in the journal Science and received the first patent for a microwave-based power transmission method in 1973. For most of the intervening decades, the concept remained confined to design studies and library shelves, largely because the necessary components, lightweight solar collection structures, and efficient wireless power transmission simply weren't technically or economically viable at anything resembling the scale required. Caltech's space solar power demonstrator launched on a SpaceX Falcon 9 in January 2023 carried an experiment called MAPPLE, the Microwave Array for Power Transfer Low Orbit Experiment. MAPPLE used an array of lightweight, flexible power transmitters to send a controlled beam of energy across a short distance to a receiver, successfully validating the core physics of the concept in the actual conditions of space. Rather than a laboratory simulation, the mission also tested an origami-inspired deployable solar structure and multiple experimental photovoltaic cell designs, gathering data that fed directly into the next generation of concepts now being pursued globally. Space-based solar power has one genuine physical advantage no ground-based renewable source can match. In the right orbit, a solar collector receives sunlight essentially continuously, unaffected by weather, cloud cover, or the day-night cycle that limits every terrestrial solar installation. That advantage has always been true. What's changed is that falling launch costs and improving lightweight solar and power transmission technology have moved the concept from theoretically interesting to plausibly, if not yet economically, achievable. The European Space Agency has approved concept studies under its SOLARIS initiative specifically to assess technical and political viability. China's Academy of Space Technology has announced plans for its own power beaming satellite prototype by 2028. Japan's space agency, the US Naval Research Laboratory, and multiple private companies are all now running active funded programs in parallel. The single largest obstacle standing between today's small demonstrations and a genuinely useful power station remains launch cost and mass. A gigawatt-class orbital solar station would require millions of kilograms of hardware placed in orbit, an enormous logistical undertaking under any current launch pricing. Every series program active in 2026 is implicitly or explicitly betting on the continued maturation of fully reusable super heavy launch vehicles to bring costs down to a range, roughly $100 to $200 per kilogram, where the economics of a station at meaningful scale finally flows. It is worth grounding this is the actual physical scale involved because it's substantially larger than most renewable infrastructure people are used to picturing. A commercial scale station would involve solar collection structures spanning kilometers in orbit, beaming power down as a low intensity microwave signal to a ground receiving antenna, called a rectenna, potentially several kilometers in diameter. The power density of that beam is deliberately kept low enough to be safe, which is precisely why the receiving footprint on the ground needs to be so large. The genuinely encouraging engineering detail here is that a rectenna's structure is sparse and low-rise by design, meaning the land underneath can plausibly continue to be used for agriculture or grazing simultaneously. Early studies on this kind of dual land use, sometimes called agrivoltaics, under rectenna are described as encouraging. So the same sitting challenges, environmental review, land acquisition, local opposition, that affect any large terrestrial energy project would still supply in future. The credible near-term trajectory based on currently funded programs looks roughly like this. Through 2027, multiple demonstration missions, including further work from Caltech, Japan's JAXA, and the US Space Force SSPIDR Arachne project, are expected to progressively close the loop from watt-scale to kilowatt-scale orbital power beaming. Private companies, including Etherflux and Virtus Solis, are targeting the first commercial demonstration satellites around 2028 through 2029, likely selling initial kilowatts of beamed power to early specialized customers such as defense installations or remote industrial sites where conventional grid access is difficult. A genuinely gigawatt-class commercial station remains on every credible current roadmap, a late 2030s prospect at the earliest, not an imminent one. But the notable shift is that every intermediate step between here and there is now identifiable funded hardware on an active development roadmap rather than a purely theoretical concept. Even short of a full commercial station, the intermediate applications carry real strategic value worth tracking now. A satellite capable of beaming a few hundred kilowatts to a specific, precisely targeted ground location, a disaster relief site, a remote military installation, an off-grid industrial facility, would be commercially and strategically useful well before gigawatt-scale grid power becomes economical. Giving this technology a realistic near-term path to relevance rather than requiring the full decades-away vision to materialize before it produces any value at all. 60 years separate Peter Glaser's original 1968 concept paper from Caltech's small satellite successfully lighting up two LEDs with power beamed across open space. That gap is a useful reminder of how genuinely long horizon energy engineering can take to mature, and also of how quietly, incrementally, the pieces of an idea, once dismissed as science fiction, can resemble themselves into something that starts one demonstration at a time to look inevitable. Thank you so much for your presence. I'm really looking forward to see you in the next deep dive. Till then.